Hi, welcome back. This is Ken, and we're still in our course on mechanics. And this is lesson 4 of the course, which is all about Newton's laws of motion. In this lecture, we're going to discuss about the concept of force, and we're going to discuss the three laws of motion that Newton formulated. And on the last part of this lesson, I'm going to teach you about free body diagrams. And this will be our goals for this lesson. First, we're going to understand the meaning of force in physics, and we're going to view force as a vector and learn how to combine forces. Third, we're going to understand the behavior of a body on which the force is balanced, that is your Newton's first law of motion. And we're going to learn the relationship between mass, acceleration, and force, which is stated in Newton's second law of motion. And we're going to relate mass and weight and see how your mass and weight differ. And we're going to see the effect of action-reaction pairs, which is your Newton's third law of motion. And lastly, we're going to learn how to make free body diagrams. We begin our lesson with force and interactions. In the previous lessons, we've studied motion in 1, 2, and even up to 3 dimensions. But so far, what causes the motion was not investigated, or we do not know yet what causes the change in motion. Like say, for example, consider your free fall. We know that when you drop an object from a certain height, the object falls towards the ground. But what causes this object to fall towards the ground? So in the past lessons, we did not study this about yet. And this causality was actually first understood in the late 1600s by Sir Isaac Newton. Perhaps you know him as someone who was hit on the head by an apple while he was sitting under an apple tree. But of course, this is just a legend, and I think I believe that there is no truth behind this. But of course, the apple is connected to Sir Isaac because this has been very important to his understanding about the universe. Sir Isaac Newton formulated the three laws governing moving objects, and we know this one as your Newton's laws of motion. The Newton's laws were deduced from huge amounts of experimental evidence. And these laws are simple to state, but they're actually intricate in their application. And we'll know the application of your Newton's laws in the next lesson. But we have here a pit crew member on a car racing. So as you can see in the figure, this pit crew member is pushing a race car forward. But we have here a question. So we're posed here a question about, is the race car pushing back on him? If so, does it push back with the same magnitude of force or a different amount of force? Okay, so again, you have here, or you were posed here a question about a pit crew member pushing a race car. So is the race car pushing back on him? If it is, or if so, does it push back with the same magnitude of force or a different amount? Or does it really push back the pit crew member or not? And we'll answer this one later as we end this lesson. But before that, let us discuss what your force is. So what forces are. So perhaps in your elementary or on your high school years, you've defined force as something that is a push or a pull. But of course, this is not an enough definition of what force is. A force is actually an interaction between two objects or between an object and its environment. Again, a force is an interaction between two objects or between an object and its environment. And a force is a vector quantity. It has both magnitude and direction. Like say, for example, here in the figure, you have a push and you have there a line with an arrowhead. So to state where the force is being applied, and you also have a pull. As you can see here, the push and the pull are actually just the same force, if you're going to apply this force with the same magnitude, they are just actually the same force pointing in the same direction. So there's no difference between your push or your pull. That's why your push and pull definition of your force is not an enough definition of our force. Instead, it's an interaction between two objects or between an object and its environment. Now we have four common types of forces. These are your normal force, your friction force, and you also have your gravitational force, and then your tension force. The first type of this force is we have your normal force. So the normal force, which we sometimes represent with this symbol N, or yeah, that N here. So the normal force is when an object pushes on a surface, the surface pushes back on the object perpendicular to the surface. And your normal force is actually a contact force. So consider this figure here. You have here your surface. See, this is your surface, and we have, say for example, here a box on the surface. Now, this object here actually pushes some force or applies a force downwards. So you have this force here by the box. So force by the box. Okay. Now, the surface also pushes the box upward. Okay. So you have here this force here N, and this force is what you call the normal force. It's also called, or it's normal because it is perpendicular to the surface. Other term for perpendicular to the surface is, we call this one as normal to the surface. So your normal force is always perpendicular, by the way. This is always perpendicular to the surface. Always perpendicular to the surface. So whatever the orientation of your surface is, the normal force is always at 90 degrees, or is perpendicular, or is normal to the surface. So here, it's clear that your first figure, it's clear here that you have here at 90 degrees, and you have here your normal force. On the second figure, and the figure to the right, your surface is oriented like this. So you have a little slant on your surface. And if you want to determine the normal force, again, your normal force is always perpendicular to the surface. This is your surface here. The box pushes the surface at this towards this direction, and your surface exerts a force which is equal to the force here of the box, and this force that the surface applies on your box is what we call the normal force. And again, your normal force here, this is at 90 degrees with respect to the surface. So it's always perpendicular to your surface. So again, your normal force, whatever the direction of your surface is always perpendicular to your surface, or at 90 degrees. Or this is at, again, 90 degrees. Okay, so that is your normal force. The second type of force is we have your friction force. So this force occurs when a surface resists sliding of an object and is parallel to the surface. Okay, friction is again a contact force. Consider here again your figure. You still have your box, and let's say that your box moves to the right. So you have the velocity of the box towards the right. Okay, so there is a motion of your box towards the right, and as you can perhaps as you have observed before, there is something that resists this motion of the box especially when your surface is wrapped. This force that resists the motion of the block, or which resists the sliding of an object, is what you call your friction force. And we usually denote your friction force with an F symbol. Okay, an F with an arrow above. And this is parallel to the surface, always parallel to the surface. if your normal force is perpendicular to the surface, your friction force is parallel to the surface, but it is always opposite in direction with your motion. So again here, if your object moves to the right, or if we push this object here with an F to the right, the resistive force which this box experiences is to the left. So the friction force is parallel to your motion or parallel to the surface, but is in opposite direction to your motion, to the motion of your object, because it resists the motion of your object. So by the way, sitting on a chair or standing up on the ground is impossible without your normal force and then your friction force. Imagine if you don't have your normal force. So when you stand up, okay, if there is no normal force, if the ground does not apply a force to your body, so when you stand up on the ground, you just fall downwards because the surface does not apply any force on you. That is also the same case with sitting on a chair. So if the chair does not apply a normal force to you, so you'll fall down on the chair. And if the ground does not apply a normal force on the chair, both you and the chair will fall down towards the ground or downwards down the hole. And without friction force, standing or walking or driving a car is impossible, because imagine if there is no friction, everything else will just slide. So this is the importance of your normal and then your friction force. So the third type of your force is we have your tension force. So a tension force, which we usually represent with a T, a big T, with an R on top, is a pulling force exerted on an object by a rope or a cord. This is again a contact force. So any force that is, or anything that is related to ropes, to springs, to cords, to anything that you can stretch. Okay, so these are the forces that are involved with this is your tension force. Okay, so again, anything that is related to, or any force that is related to cords, to springs, to ropes, anything that you can stretch, we're referring to this force as your tension force. Okay, and the last common type of force is your weight. So the weight is actually a force. So the weight is the pull of gravity of an object, and this is a long-range force. Okay, so the reason why in free fall, when you drop a body from a certain height, your body falls downward because of the force due to gravity. So this time we have take into consideration what was the reason behind why your free fall, or why your object falls downwards with when you drop it from a certain height. So we've talked a lot about your forces, but how do we quantify these forces? Force is a quantity which is measured using the standard metric unit, which we know as your Newton. Okay, of course, this is named after Sir Isaac Newton. A Newton is abbreviated by an N. To say 10N, it means you have 10 Newton of force. 1 Newton is the amount of force required to give a 1 kilogram mass an acceleration of 1 meter per second or 1 meter per second squared. Thus, your 1 Newton has an equivalency which is stated by the following. You have 1 Newton, this is equal to 1 kilogram times 1 meter per second squared. So all your forces, we have your tension force, your friction force, your normal force, and even your weight has a unit of newtons. So interestingly, your weight should have a unit of 1 Newton. So I think this is a common mistake among Filipinos when we say that when we're asked about our weight, and we say that our weight is 50 kilograms, where in fact, kilograms is not a unit of force, and weight is a force. So when we are asked about our weight, we should state something that is connected to the kilogram, or sorry, related to the Newton. Okay, so we'll correct this one later. Let's try to find an equivalent of your mass. Okay, we call that one as your mass, 50 kilogram. An equivalent that we'll find an equivalent to this one so that we can use it in terms of weight, which is in Newton. These are some of the typical force magnitudes. So this is just for you to know how you compare your forces exerted by different objects. So, like say for example here we have the weight of your apple. Okay. The weight of your apple is around 1 Newton. Okay. And the weight of the smallest insect eggs, you have 2 times 10 to the negative 6 Newton. So that's very, very small weight. Let's go to bigger bodies. Like say for example, the weight of a large blue whale, that is 1.9 times 10 to the 6 Newton. And you have the sun's gravitational force on the earth, that is around 3.5 times 10 to the 22 newtons. The weight of an electron is 8.9 times 10 to the negative 3 Newton. So these are some of the typical force magnitudes of your bodies. And again here, we have here, you've seen or you've observed about the weight. And for the unit of weight, we did not use your kilogram because the kilogram is not a unit of your force. A kilogram, again, is not a unit of your weight. So let's correct this one next time. So again, since force is a vector quantity, we use your vector arrow to indicate the magnitude and direction of your force. So you can draw your forces again on the x, y, and z plane. Like say for example here we have a pool, a 10 Newton pool directed 30 degrees above the horizontal. So this is this arrowhead here, this vector arrow points to the pool, a pool of 10 newtons, and this is directed at 30 degrees above the horizontal. So you have an arrow that is about 10 newton, and then you have your angle, 30 degrees. Another one is you have your 10 newton push directed 45 degrees below the horizontal. So as you can see, since the force here is applied towards the box, okay, at 45 degrees, the arrow is pointed towards the box here. Okay, so whatever direction of your force vector is, that is also the direction of your arrow. So this is just the same concept with what we have learned in lesson 1 on vector quantities. So we have this concept, or we have this principle, which we call the principle of superposition of forces. So what's this superposition of forces all about? So when several forces are acting at a point on an object, like say for example here, let's consider this point here at O. Okay, let's take into consideration this point here. When we have several forces acting on this point, it has actually just the same effect as their vector sum acting at the same point. So what we mean here is that if you have here your force 1, we apply two force 1 and force 2. Okay, we apply two forces, force 1 and force 2. These two forces actually has the same effect with this resultant force here, or the sum of your F1 and F2. It's the same way as saying as if you are here, excuse me, if you're here and then you are pulling the box, Okay, you pull the box here, and then one of your friend is up here, and she's pulling the box upwards towards this direction, while you are pulling the box to the right. Okay, the force that the two of you apply is just actually equivalent to one force, which is like this one here. This is equivalent to one man pulling the box with this amount of force with this at this direction. So that is your superposition of your forces. A classic example is you have your tug of war. So you have here you have 6 forces, right? So let's say you have your F1, F2, F3, F4, you have your F5, and then your F6. And of course, these forces are at different directions. Let's say one is pulling there, and then the other is pulling a little there, and then the other is pulling a little there. And let's say you have this one here, someone is pulling around there, and someone is pulling around that direction. So the forces that this, let's say on the right side here, the forces that these 3 kids apply on the tug of war is actually just equivalent to having one person pulling the rope, okay? One person pulling the rope, and this person here applies the same force, which is equivalent to the sum of these 3 forces here. So we can represent that one as just one man. That's why in a tug of war, your team should have the same direction of, should apply the force in the same direction, so that you can maximize your pull. So you'll win. Otherwise, if one is pulling like this, one is pulling a little downwards, one is pulling a little upwards, and one is pushing straight to the left, the sum of these forces will not be a maximum. Okay, this is if you played tug of war before, you know that all of you must pull at the same direction, which is here, the left. The same is true with this one here, with your players on the right. This is just equivalent to having one person pulling the rope to the right. This other person here pulls the rope to the left. So that is what that's why in a tug of war, unity is very important. So when we say unity, all of you must apply the force at least at the same direction to maximize the force. And lastly, so we have this one here. So we have sum this one. We have sum your 3 forces to the left, and you also sum your 3 forces to the right. These 6 forces, if you're going to sum that one, that is just actually equivalent to these 6 forces is just actually equivalent to having one man, let's say, pulling the rope. And you know that the team that will win in the tug of war is the one which applied the larger force. If let's say this is the force to the left, and the force to the right is this big here, okay? If we're going to sum these two, this is a negative force, and this is a positive force, but your force to the right is greater than your force to the left. So you know here that the team on the right wins the tug of war. So it's just actually equivalent to having one force. So your F1 plus F2, your F1 plus, or your F left plus your F right is just actually equivalent to one force, F, or the winning team. So that is your superposition of your forces. And if you have your superposition of forces, we can also decompose a force into its component vectors, just like what we have learned in lesson 1. So we have here your, if let's say you have here your vector force F, okay? This vector force here, if you're going to resolve that one, we draw a wiggly line, okay? We draw a wiggly line here to to represent that we have actually resolved the force into its x and y components. So projecting it on the x-axis, it has an fx, its component on the x. Projecting your force along the y-axis, you have this component of your force on the y-axis. So your single force that you applied here at an angle theta is also equivalent to having two forces. One is pulling to the right and then the other is pulling to the left. And if you're going to sum these two forces here, you'd expect that your block or your box will move in this direction here, which is your F net or your net resultant force. So this is the notation for your vector sum of your forces, just like your vector sum in lesson 1. The vector sum of all the forces of an object is called the resultant of the force or the net force. So sometimes here we'll use your R for your resultant, or we also represent this one as your F net, or just a simple F. Okay, and these are some of the notations for our resultant or for your net force. Like say for example here we have two forces. You have here your F1, and then you apply another force F2. So these two forces here, by the superposition of principle, is just equivalent to having this force here. If you're going to connect this, if you're going to decompose these forces, you have here your F1x, and then you have your F2x. You have here your F1y, and then you have here your F2y. The sum of this one is just actually equal to your Ry and then your Rx. Okay. So let's have an example. So 3 professional wrestlers are fighting over the same champion's belt, but instead of wrestling, they've decided to determine the winner of the wrestling by a tug of belt. So they're trying to win over the wrestling match with pulling the belt towards their side. So 3 professional wrestlers are fighting over the same champion's belt. So as viewed from above, you have here your figure. As viewed from above, they apply 3 horizontal forces to the belt that are shown in the figure. The magnitudes of the 3 forces are F1, you have 250 Newton, F2, you have 50 Newtons, and F3, you have 120 Newtons. Find the X and Y components of the net force on the belt and find the magnitude and direction of the net force. So again here, instead of playing the match with a wrestling, instead of doing an actual wrestling, the professional wrestlers decided that in order to win the belt, they're going to pull the belt towards their side. And the one who pulls the belt towards their end wins the championship belt. Okay, so F1 here, this is directed 53 degrees north of west. So it has a magnitude of 250 newtons. F2 is pointed towards the east, and it has a magnitude of 50 newtons. And lastly, your F3 is pointed to the south, which has a magnitude of 120 newtons. So our target here is to find the X and Y components of the net force in the belt and find the magnitude and direction of the net force. So where do you think where will the belt go? So in what axis, or who will be more favorable to get the champions belt? So let's solve this problem. So again, we're given with your forces, your force magnitudes, and you have here your figure. And just like we did in lesson 1, I've drawn here a force table. Okay, so that it will be easier for us to sum your forces. And let's start with your force 1. Okay. Your force 1 is directed 53 degrees. That is north of west, so it has some angle. So there's two ways to find the components. We either use your 53 degrees here, but we take note that here your F1x should be negative and then your F1y should be positive, or we can also use this angle here. Okay. But let's just use your 53 degrees. So projecting along the x-axis. So you have here again a wiggly line. A wiggly line represents that you're decomposing your force into its x and y components. So we project this one on the x-axis. You have here your F1x, which should be negative. So solving, that is an adjacent side. So you have your F1x, that is negative of your force, which is 250 newtons. And then we have cosine 53 degrees. So we have put here, I put here a negative on your solution, because if you're just going to put 250 newtons cosine 53 degrees, you'll notice that you get a positive answer. But basing on the diagram, you know that the force should be, or the x component of the force should be negative. So that's why I put here a negative mark. Solving this one using your calculators, you get an answer of around 150 newtons. So your x component is 1. Let me erase it. So you have 150 newtons. So your F1y, projecting it along the y-axis, you have here should be positive. So you have, that is an opposite side. So you have 250 newtons and then sine 53 degrees. So we have here around 200 newtons. Sorry, this is negative. So that is your F1 decomposed into its x and y components. Next, we go to your force 2. So your force 2 is just directed towards the east. So we have 50 newtons. And we do not have a component along the y, so that is 0. So that was easy. So let's go to F3. So your F3 is directed to the south. So your x component is 0. And then we have here a negative 120 newtons. So your F net, or your resultant force, or your R, let's just call this one as your F net. This is equal to the sum of your x component, your x's. So that is negative 150 plus 50. So you have negative 100 newtons. And for your y, this is sum of your y's. You have 200 plus negative 120, that is 80 newtons. So the x component, you have your F net x, or your Fx. Sorry, this is not a vector yet. Your F net x, the x component, this is negative 100 newtons, and then your F net y, that is equal to 80 newtons. So what's the magnitude of your force? So I'll just leave it to you. Of course, you're just going to use your F net, that's equal to the square root of your F net x squared plus your F net y squared. Okay, so you can solve it already by yourselves. Again, this is F net y squared. And you're going to find theta. Okay, so you can either have this By the way, let's draw this your F net. So it has a negative x and then positive y. So let's say you have here, this is negative 100 newtons, and let's say this is 80 newtons. So this is here your F net, somewhere around here. And your target theta is this one here, or you can also use this angle here. It's up to you. So you can solve it, and you find that you have, if we're referring to this theta here, you have, you can get an answer of 39 degrees north of, this is north of west, or this is equivalent to 141 degrees measured from the positive x-axis.